today I'll be presenting on skip list, fascinating and probabilistic data structure that serves an alternative to the balanced trees. So the skip lists are used in real world systems like Redis and the level database. And by the end of this presentation, you'll understand why there's such an elegant solution to the problem at stretching and sorted data. Uh, What problem does the skip list solve? Let's start by understanding the problem the skip list is designed to solve. So imagine you need to store data and search through it quickly. This is a common requirement in databases and search engines and many other applications. Now, linked lists are simple and easy to implement, but they have a major drawback. Searching requires O of n time. This means if you have 1,000 elements, you might need to check all 1,000 nodes in the worst case. On the other hand, the balanced trees like AVL trees or red-black trees gives us an O of log n search time, which is much faster. However, these structures are complex to implement and they require rotation algorithms and strict balancing rules. It's way simpler and more elegant code, and which is simple to understand and not that complex. And this is exactly what the skip lists accomplish. And the real world uses are, you might be wondering that why not just use the balance tree if they have already solved the problem? Well, the balance trees require complex rotations and rebalancing after insertion and deletion. The code can be difficult to write correctly and even hard to debug. Skip list achieves a same of log n performance with much simpler algorithms. There are no rotations, no complex balance rules, just straightforward pointer manipulation. Additionally, skips the list is easier to implement in concurrent and thread-safe versions, which is crucial for the modern and multi-threaded applications. This application isn't just theoretical. The skip lists are used in production systems today, like Redis, and in-memory database like skip list for sorted sets, and level database, and even which level database is a Google key value storage engine, also relies on them. You will also find Apache, a search engine library, and the memory SQL, which also can MemSQL, a distributed database system. So these real-world applications prove that the skip lists are both practical and performant. Skip lists. Skip lists were invented by William Pugh at the University of Maryland in 1990. His work was published in the prestigious Communications of AMC Journals. Pugh's goal was to create a simpler alternative of balanced tree instead of using the deterministic balancing rule like AVL or red-black tree. He introduces a probabilistic structure that is much easier to understand and implement. The key innovation was using randomization instead of like strict balancing algorithms. This trade-off using the probability instead of the guarantee, what was make the skip list so elegant. And here's a fun fact: the name skip list comes from the ability to skip over many nodes during the search operations, which we'll see in the action shortly. So the skip list structure. The skip list structure. Now we look at the what a skip list actually looks like. A skip list is essentially a layer of linked list. Think of a multi-linked list that's stacked on top of each other. At the bottom is the level 0. All we have is elements stored in a sorted order, which is like a regular linked list. An example, we can see here we have the values 2, 8, 10, 11, 13, 18, 20, and 21. But here's where we get interesting. The higher level that contains only a subset of these elements, this higher level act as an like an express lane, like in highways, like is an express lane that let us skip over many of the nodes during the searching. Each node has a multiple forward pointer. One of each level a node appears at level 2 must also appear at level 1 and 0 below it. Notice the sentinel node on the left. And this is the special head node that exists at all levels and mark the beginning of the skip list. The height of each node is determined randomly when we insert it, and which we'll discuss more in a moment. List properties. To maintain a valid skip list, we must preserve certain properties. First one is the order, the sorted order, sorry. Element at level 0 must be in increasing order. That is fundamental. The second one is the level subset property. If a node appears at level k, it must appear at all level below k. Level 3, it doesn't exist in level 2 and level 1, 0. We'll see in when we do the animation, the practical, I'll show you, you can see these examples over there. On the third node height, we have chosen randomly using a coin flip approach, which we'll demonstrate during the insertion. And the level distribution follows a specific pattern. Approximately 50% of the nodes have a height of 1, and 25% of have height of 2, and 12.5% have a height of 3. In general, the probability that a node is height k is 1/2 of the power of k. This probabilistic distribution is what creates a pyramid-like structure and ensures a good performance. Express lane on a highway. So this is what we have, an express lane analogy. To build an intuition, it's like a thinking of us using a highway system analogy. Level 0 is like a local road. You stop at every single house, visiting every single node. Like we have the stadium way here in Poland. You only stop at the major intersection and skipping over some nodes. Level 2 is the highway, the connecting cities, skipping even more nodes. And level 3 is the interstate, like the I-90 we got, only stopping at the major destinations. That's how we divide our different levels in a skip list. And the search strategy is simple. Start at the highest level, move airport as the next value is less than your target, and when you can't move forward, drop down one more level. Repeat this process until you either find your value to reach the end at level 0, and this express lane approach what gives us a 0 of log and search. Going to search the value of 8 in our skip list. Watch carefully as we navigate through the levels. Final node at the highest level 3, with our goal is to find the value 8. We'll look at the next node, which is 13. Since 8 is less than 13, we cannot move forward at this level. So what we do? We drop down. We drop down since 8 is less than 13, we drop down. And now, still, look at the sentinel position. And as we know, the 8 is greater than 2, so we can move forward to the next node 2. Now, 8 is less than 13, so we cannot move forward. So we drop down to level 1. Level 1 node is from 2 is 10, and 8 is less than 10, so we cannot move forward. So we drop down to level 0. At level 0, the next node is 8. We found it. The search is complete. So did you notice how we only examined a few nodes? The Sentinel, 2, 13, and 10. Before finding 8 in a regular linked list, it would be a check the Sentinel and 2 before finding 8, but a larger linked list skips lists, but in a larger linked list, it'll be a chaos to find 8. So skip list save us from checking many of the other nodes that we don't need. And this is the power of the express lane analogy. Okay, let's move forward. Let's move forward to insertion. Now it's gonna see insertion in action. First, we'll insert value 18 in our skip list. The process involves two main steps. First, finding where the new element belongs, and the second, determine how tall the new node should be using randomization. Values 2, 8, 10, 11, 13, 19, and 20, and 22. We're going to insert 18 as it states up there. So first, we perform a search to find where 18 belongs. It works exactly like the search operation. Starting at level 3, checking against 13 and 18, which is great, so we move forward. At 13, the level 3, so we see 19, and 18 is less than 18, so we drop down. Okay, it works now. Uh, Checking against 18, the 18 is greater, so we move forward. And again, we see that it's the key is greater than 18, which is 18. We move forward, and again, like so, we drop down. Where the 18 would go across each level. Now in the skip list, we use a technique known as the coin flip technique. Remember, from our introduction, we have referred this as the data structure relies on the randomization, where we got the principal form. Where the element would go across each level. We essentially flip a coin. If we get head, we move increase the level. If we get tail, we stop right there and insert not at the position. Assuming we have landed at level 2, we'll see how this element will be inserted from now. Where the 18 should go and 13 and 19. But how we should the new node be? Okay. Let's skip list uses a coin flipping technique. We flip a coin, and if it is the head, we conclude this node as the next level up, and if it tails, we stop. For example, let's say we flipped a coin, we got a head of level 1 and head of for 2, and that tail. So our new node would have a height of 2. Remember, the randomization is what creates the probabilistic balance in skip list. About 50% of nodes will have height of 1, 25 will be height of 2, and so on. And let's move on and create a node 18 with a height of 2 and update all the pointers. As you can see here, we have successfully inserted 18 up here. We have successfully inserted 18 up here, and there we have now 18 is successfully inserted at level 0, 1, and 2. And the skip list maintain all the properties and remain sorted. Let's move forward. Now let's discuss about deletion. Finally, we look at deletion. We'll delete the value 2 from our skip list. And the process is straightforward. Find the node, update the pointer, bypass. 2, we start searching from level 3. At level 3, and 2. So now 13 is greater than 2, and 2 is the key here. 13 is greater than 2, so we drop down. As we know, if the node is greater than the key, we drop down. At level 2, we immediately find 2. We recorded these positions because we'll need to update the pointers here. And now we move forward and we delete. So we simply remove the element from the level connecting the pre-deciding node to the next accessible node. If any would be deleted operation, in example that follows, we will update a prevalent misunderstanding regards the level in skip list. We started searching for not for our uh, for the to deletion and we found it and we deleted it. So we'll see what happened next. Time and space complexity. The time and space complexity and analyzes the complexity of skip list operations. And deletion the average case of O log n. This is because expected path length to the level of logarithmic. At each level, we only examine the constant number of nodes before dropping down. However, the worst case for all three operations would be O of f O of n. And this happens if we are extremely unlucky. And with randomization, all nodes and the end of the hike one, it's degenerating into a regular linked list, but the probability of this incredibly low. Average case 0 of n with an expected total of 2n pointers across all leads. The worst case is O of n log n if every node happens to reach the maximum height. The key insight is that while skip lists don't guarantee all flag and its balanced tree, do they? But they achieve it with a high probability. Simpler structure is how it looks. As we have here the skip list, the balance trees, and the hash tables. So we have some features like search, order, range queries, implementation, concurrency, and memory. And balance trees have O of log n search times, while hash tables is offer O of 1 average search. Limitations: skip list and the balance tree maintains order data, and making range queries easy. We need all the values between 10 and 50. Just traverse from 10 to 50. Hash tables don't maintain order, so range queries are really difficult. Skip lists are simple, no complex rotation logic, balance the BST or binary search trees, and the complex is their rotation algorithms. The hash tables are relatively simple but require good hash functions. Skip lists are excellent because the log-free implementations are possible, and this is much harder with balanced uh, binary search trees. The trade-off is memory. Skip list uses about 2n pointers, while the binary search trees uses the n pointer. Hash tables are very depending on the implementations. List. So this is what we call the advantages of skip list. First, we have when you want a simpler implementation, there is no complex rotation logic like AVL and red black trees. The code is easier to understand and very easy to debug. This example, excellent concurrent access, lock-free implementations are possible, making them superior to the balanced tree in multi-threaded systems. Like we talked about, Redis uses them. Third, they offer predictable performance. You get off log n with a high probability, rebalancing, and delays that can occur with balanced trees. Finally, they're efficient, the range queries because the data is naturally ordered at level 0. The list scripts are perfect. Let's discuss about how to way to avoid them. First, they have a higher memory usage requiring about 2 endpointers to the average, which is more than the balanced BSTs. Endpointers, if memory is tight, this matters. They do not deterministic performance depend on the randomization, while worst case of an extremely unlikely. Balanced trees guarantees all of log n. Shape performance. It can be an issue. The pointers are scattered in memory, unlike the arrays or B trees where the data is contiguous. Performance in modern CPUs and that relies on heavily on cache. Where skiplets in memory is very tight, you need to guarantee a worst case performance, and cache locally is critical. In which case, consider B-tree instead of skip list. Practical implementation. If you're implementing skip lists, here are some practical considerations that we should consider before implementing them. First, choose a maximum level. A common choice is log base 2 of your maximum expected element. For example, for 1 million elements, a max level of 20 is appropriate. Parameters P, the standard is 0.5, like flipping a fair coin, but you want to use 0.25. For the less memory usage and cost is slightly slower operation. Third, use a quality random number generator whose randomness is significant to her performances. The common pitfall including forgetting the update the all during the insertion and deletion and off by one, errors in leveling count. Don't properly deallocate the nodes. And that concludes my presentation on skip list. You've seen how they solve the problems so fast and searching in sorted data it's using simple and elegant algorithms based on randomization. An example how the probabilistic approach can sometimes be simpler and more practical than deterministic ones. Thank you for watching. I hope you have appreciated the beauty and the utility of skip list. Thank you so much.